Ah, vede la persona, se no la persona viene con il fondo. Si vede questo e si vede la persona. Poi che c'è una buona... Vedi? Si vede la persona. Si vede questo?
Sorry, we are going to take a picture for me.
Ah. So you send it on Twitter?
I'll put it in the webpage.
Because
Ma comunque si vede comunque, ma lo posso chiudere completamente. Ok. Okay. Welcome everyone. So, like in every city in the world, the traffic jam ate a little bit of the schedule. So we're going to start now, and we we have the honor to be welcomed today by Maria Jesus Mosquera Diaz, who is the Vice Chancellor of Research and Technology of the University of Cadiz. And Maria Jesus will give us a little welcome speech. Thank you very much.
Thank you so much. Good morning. It's a pleasure for me to be here today. It's a pleasure to have in the open ceremony of the 30th Coastal Altimetry Workshop. A great conference, and firstly, I would like to thank you very much to the Professor Benviste and to the European Space Agency to choose University of Cadiz and to choose the city of Cadiz to organize this workshop. It's a great honor for us. And thank you very much also to the organizer, to the head of the conference, Professor Gomez-Henry, Jesus Gomez-Henry. Thank you so much. And thank you to all people of the department, of the Applied Physics department. It's a great department working in a specific work regarding to physics and regarding good coastal areas. I'm going to say welcome also to the Dean of the Faculty of Marine Science. Thank you very much to be here with us. I think you are also a participant in the conference. Thank you so much. And thank you especially to all people here. You are around 130 persons for different countries working on the same topic. I think it's also a good idea, great idea, to organize yesterday a training for young people, because the young people, the scientific people, is really important for us, for all the community, and especially in these specific technology topics. Thank you so much for coming. I hope you enjoy of this interesting topic of the workshop, and also, of course, of the city of Cádiz. You can see we have a really nice weather today, and please enjoy of the city, the history, and also I would like enjoy of the of all the food and the sea, and especially of the sea. I would like to say that this topic is really important for us. In the end of the last year of 2022, we have the very big conference regarding to blue economy in Nova Azul, with around 20,000 people working in the industry, working in science, working in different authorities, complete different people speaking about blue economy. And blue economy is really a very important topic for University of Cádiz, because we have very close to the sea, you can see here in this very amazing building. And also we have a tradition working in marine science, but also working in engineering aspects, in physics as well. This is another conference regarding to Economy Azul held in this year, and this is really important for us and for university. And also I would like to say that here today we have people working in different aspects with a common topic, but you are scientifics for university, that also engineers and also managers. And the multidisciplinary is really important in this topic and in all the topics nowadays. The coastal altimetry community is very important community, and this is today one of the first targets for the European project, for the European proposals. And the agency is really important in this project, but also is really important in the policy of Europe. That is significant that you are here together during 2-3 days speaking about the coastal altimetry topics, speaking about the novel ideas, speaking about science regarding to this topic. And I am sure that in the end of these days, you have increasing your networking in this topic, and maybe you can organize ideas for projects, for European projects, and for another international projects. So thank you very much for coming. I'm very happy to have a lot of young people here today in this open ceremony. Thank you for coming. Enjoy for the topic, enjoy for the city. And I want to say thank you again to the European Space Agency and also to Professor Jesus Gomez-Henrys. Thank you so much.
Thank you very much for this warm welcome, and I can assure you we already enjoyed the city and the quality of the welcome of the university, like the room and the cafeteria was very good as well. Okay. Very much. I will make a few introductory words on behalf of ESA. Something happened. This has disappeared. My window. Where's my window? Okay. There we go. Okay, so welcome to the first day of the workshop. But many of you have been here yesterday for the training. It's a tradition to do the training. It's like a warm-up before you do the exercise. And so I was really happy to see that at least 80% of the people registered for the training. So that was a good success. And I thank all the lecturers that came and organized this warm-up. And so where do we come from? In Venice in 2006, 15 years of progress in altimetry, we were saying coastal. The word was coastal. So we started to get organized, and at OSTST, we started having a coastal splinter. Then we could not just spend half an afternoon on the coastal subject. So the idea came that we had to do this, and we all agreed. And Ted Strubb said, "Okay, let's do it." And then and on our side, we said, "Yes, let's do it as well." So in 2008, we had two coastal altimetry workshop, one in the beginning of the year, one in the end of the year, thanks to Stefano Vinudelli, who was also very energetic in creating this event. And then we had the third one, the fourth one, and so on. And then during that time, in the beginning, the Bible came out, and a lot of people, a lot of authors, and where's the book? Again, so here you can browse the table of content, and it's a lot of people were involved. And so what I can tell you is that it has 572 citations, and it's still being acquired. So Springer is very happy with this book. Then we went on, and we had to meet regularly and so on. So in 15 years, we met at least 13 times, and this is the 13th time. And so I really thank the people and their energy that they put in this topic. So here we are today. The program is available online. It's also somewhere in the Rome airport in a suitcase, which is among hundreds of other suitcases, and they're not being dispatched, and that's since a Friday. So, we can go to the moon, we can go to Mars, but very difficult to go from Rome to Jerez. So we apologize. So we reprinted the badges, so you can pick up your badges, but the program, was a bit too heavy to do, but it may arrive this afternoon or tomorrow. Okay, so the program of the morning is this a few words and so on. Okay, so this is wrong. This is the program of yesterday. Okay, then we prepared a certificate. So we are going to try to get to you a certificate. If we can't get to you on paper, you'll get it on a PDF. The coffee breaks are downstairs. The next to the posters, you see it over the posters. You can have lunch at the cafeteria. It's on the opposite wing, and you have to just wait until 1 o'clock until you get there to avoid the queue. So on Wednesday, there's going to be this non-hosted social event, and so I'm a bit puzzled because this is not the version of the slide that I wanted to present you. Okay, for some reason. All right, so basically, it's very important that all who have registered for the dinner pay for the dinner. And the idea is that there is a 5% margin. So if people didn't register and they want to be at the social event, it would be very nice, very welcome. There's a wireless LAN, and you got an email on Sunday, so you can connect. First, you get to the network, and then you get to the university firewall, and then you type the password that you were given, and you get in. Try to avoid connecting both your cell phone and your computer and your iPad, and so on, so we can enjoy this thing. So have a very pleasant workshop, and enjoy Cadiz. And so you see, somebody closed the window, and when I opened the window again, I opened the window in the wrong territory, and this is called day one. And so I'm a bit handicapped with this type of operating system. Day two? Where's day two? Day one. So right. Ah, okay. Yeah, okay. All right. So let me just show you one slide where, okay. So, yeah, so 15 years anniversary, the Bible, we weren't there and so on. So we're going to start with a scientific session chaired by Florence Birol and David Cotton. Thanks to all the chairs that came around. What I wanted to say is that all the chairs are going to animate the discussion. And so they have produced seat questions that we're trying to get on the web right now. So stay tuned. The idea is that a workshop like this is for us, like ESA or NASA or NOAA or UMETSAT or any funding agency like the European Commission to get requirements coming from the community. So the most important part after the science that we can deliver is really the discussion and the feedback and then the report that we write. You know, thanks to these things, I've launched many contracts, like the last one we heard about yesterday, EO at sea, coastal hazard at sea level. It came from a recommendation from these kind of workshops. Okay, so we made a certificate and here. So the non-hosted dinner will be held at the Baluarte de los Martires, El Faro de Cadiz, and this is what you see on the picture. It's on the sea, there's a big terrace. If it doesn't rain too much, we can enjoy the full moon and the lighthouse. And please, all that have registered, please come because we committed to the restaurant. If not, we'll have a problem. So enjoy. So so the price is really 44 euro, and the restaurant will provide you a receipt. We decided to make it simple, 45, so we give €1 tip to the people. And tell us if, in terms of internet, tell us if you want to be added to the coastal SWT mailing list for the newcomers. Please do that. Okay, bring your presentation to here. There's no computer presentation ready, speaker ready room. We're going to put your presentation as PDFs on file. And yesterday, all the lecturers, we will put the PowerPoint on the web because I would like that they are reused for capacity building in Buenos Aires, in Cape Town, in Shanghai or whatever, any place in the world where people came from far away, and they can go home and continue propagating the knowledge that was dispensed yesterday. So most of the people agree. If you don't agree, give us a PDF or something that you customize so we can put it on the web. The posters, you put them up now, and it's really great to have a poster. If you have a poster, it's much better than a talk, because the talk, you give your talk and then it's finished and so on. In the poster, you can bring people to your poster all week long, at every coffee break, at lunch breaks, and you can start discussing in details what you have. So it's an honor to have a poster, and the poor people who have to give a talk, I'm sorry for them. Okay, and your poster is as important as your slides. So give us the PDF. We'll put it on the web. So please send the PDF of your poster to events.organization@esa.it. So have a pleasant and successful workshop, and thank you very much. I leave the floor to science. And Florence and David, please come up and take over stage. And I'd like to thank what I call the sponsors. Basically, it's all the people that have worked for creating this event. And of course, I would like to thank Professor Jesus Gomez Henry for having volunteered to invite us here. And I thank the university in the name of the Vice Chancellor for hosting us. Thank you very much. So, as part of the opening session, and then you will chair, we have a keynote, and let me introduce the keynote speaker in the person of Sonia Ponce de Leon, a famous navigator. And so Sonia, as part of the opening session, you have 30 minutes to give us a talk on waves. And why waves? Because I think that in the past, in the 12 coastal altimetry workshop of the past, we didn't insist too much on wave. And so I think it's a good topic, especially that we're talking about extreme events, we're talking about wave setup, we're talking about wave wash up, and we'd like to know everything about waves. Sonia, please, you have 30 minutes.
No. Thanks. Thank you very much, Jeroen. I am very happy to be here, and also I would like to congratulate all the organizers of the workshop, and in particular to Jeroen Benveniste, because he decided to include a session of waves, and I take this opportunity to invite you to attend it on Friday. So waves in coastal zones are very important for many reasons. There is a destruction when big waves arrive to our coast. In addition to this, in the context of the present crisis, energy crisis, we need to recuperate some energy from waves. And in this context, high-resolution simulations in the coastal zones are needed. So wave modeling is a great art containing two main aspects of human knowledge, which are theory and practical applications. I will follow this content, and at the end of all, I will give some outlook and recommendations. The state of the art of wave modeling presently faces some challenges, and in particular, we need to understand better and to represent in our models the wave breaking, which is associated with the wave energy dissipation. And also, all of the integral parameters are very well represented in our models, but we need to research more in order to get better representation of the bidimensional high-frequency tail of the wave spectrum. In addition to this, we need to understand better how our wave reacts when a string wave in front of wind wave. And in this sense, we need to inspect more, to get more improvement at very high resolution, higher than 35 meters per second. Apart of that, we also need to know how to use the wave information when wave interacts with other processes, such wave current interactions, wave ice interactions, air-sea fluxes. And also, I would like to take this opportunity to advertise the 4 workshop on wave that will take place next week in Sweden. In addition to this, I would like to advertise the WISE meeting, which is the most important meeting of the wave modeler community, which will take place in US in May. Apart of this, I would like to advertise the ERC Advanced Grant High Wave of Professor Frédéric Diaz from UCD and École Nationale Supérieure de Paris et Saclay. They are researching new formulations for the wave breaking, and I think that this project will give very good, interesting results for the community. So coming back to the story of wave modeling, I would like to point out that in the 60s, were developed the first generation wave models that avoided the problem of explicitly modeling the complete energy balance. So in the 70s, were developed the second generation wave models that were unable to simulate complex wind seas, such those waves that are developed in situations of hurricanes or extratropical cyclones or cold fronts. And finally, in the 80s, appeared the third generation wave model that don't apply any restriction for the evolution of the wave spectrum. It was in 1988 when was developed by Hasselmann and other colleagues a particular parametrization in order to estimate the four nonlinear interactions, which is the discrete interaction approximation that is implemented and used in all the operational wave forecast system presently. So here you have a list of the most known spectral wave models, but also I would like to point out that the model was the one model. So also there are several other models, of course. And this is the energy balance equation that describes the evolution of the wave in the ocean surface. The wave spectrum represented by F as a function of the position, frequency, direction, and time. The first term represents the evolution, the local evolution of the wave spectrum, and the CG is the velocity group at which the information travels along certain geographical domain. And to the right hand are included all the physical process that allow that wave increase or dissipates. And this is the Boltzmann integral that it is used for computing the four nonlinear interactions, and the main role of the nonlinear interaction is the redistribution of the wave energy in the frequency domain. This is the wing input source term. This function is proportional to the product of the frequency and the wave spectrum, and this is the wave energy dissipation composed with which has some different contributions. In the deep waters, the dissipation of the wave energy due to the white capping. In the shallow waters, the dissipation due to bottom friction and also due to the breaking. So in order to compute the four nonlinear interactions, we have several methods to do it, and these listed methods are already implemented in the WaveWatch3 model, which is the state-of-the-art model, and because it has a lot of resources in order to develop this code. And I would like to focus your attention on the first and the second one. The first one I already mentioned earlier. This is the discrete interaction approximation that all the operational wave forecasts are using right now. And the second one is the full Boltzmann integral method called WRT. So if we compute or if we estimate the wave spectrum using the discrete interaction approximation, we are underestimating the wave spectrum. As you can see on the left is a comparison performed from wave spectrum from the WaveWatch3 model against a Doppler radar and measurements, and in the North Sea in the SlateNet platform. And to the right hand, we have a perfect match of both wave spectra if we use the WRT method, which is the exact nonlinear interactions method. So when we speak about a spectral wave model, we need to know that we have a spectral description of the wave field at each grid point of certain region. So to the left hand, we have to the left side, we have a coarse grid encompassing the North Atlantic, and in the middle, we have a nested grid encompassing this portion of the ocean, including the North Sea. And this is a bidimensional wave spectrum obtained from the wave tree simulations at Sleipner. So wave current interaction in the Agulhas current is also a very interesting subject that is being investigated by several researchers. As you know, at a scale of around 100 kilometers, wave is modulated by current, and this modulation accounts for about 75% of the spatial variability of wave height. Also, there are some investigations running about the generation of a string wave as the results of the wave current interactions. So this is some validations performed for this nested grid using satellite altimetry in this case. This is a scatter plot after the collocation between the JSON tree significant wave height and the one model significant wave height, and some statistic in order to note to have some information about the goodness of the numerical simulation performed. And to the bottom, some comparison with the wave buoy. I would like also to point out that in this region, we don't have many wave buoys, unfortunately, but we have several beautiful altimetry products and SAR images, so this is a good point. So data simulation in operational wave forecast is very important, and weather and ocean depends on initial conditions, and many of the operational wave forecasts of big centers are using the data simulation from the SAR swell data and the CIFOSAT wave spectra. So in particular, ECNWF is performing data simulation from altimeters since the 90s, and unfortunately, because of the lack of some resources, the progress lately is not very noticeable, but they have been assimilating Sentinel-3, Sentinel-6, JSON, and Cryosat and Saral Altica. And if you see in this graph, the bias is low when we have low significant wave height, but as soon as the significant wave height increases, so the bias also increases. So in particular, ECNWS F is obtaining some improvement for the northern hemisphere. This is during the first day, forecast day, and this is about 3%. And on the case of the tropics, the impact of assimilation is higher. And coming back to coastal zone, this table represents the dominant and the significant but not dominant physical processes that modify wave in the coastal zone. So on the case of a harbor, for example, the dominant processes are reflection and diffraction, and on the case of near shore, the dominant process are the bottom friction, shoaling, and breaking. So this is an example taken from a nested grid simulation performed in the Mediterranean Sea, and as you can see, refraction makes that wave turns toward the coast. And this is another example of a nested grid on the Portuguese and Spain Atlantic side. And as you can see nearby the coastal zone, there are some spots showing the shoaling. And there are many other additional processes that take place in the coastal zone, which are the bottom friction dissipation and the wave breaking, and also the triad interactions. When I showed earlier the energy balance equation, I choose the example for deep waters because it's a simple equation, but on the case of the shallow water, we cannot ignore anymore the reflection or the diffraction or the wave breaking. So the energy balance equations uses the Eulerian approach as well as for the deep waters, but is more complex, and also the source terms. So when we speak about the near-shore wave prediction, we need supercomputing resources in order to develop this kind of computations, depending, of course, of the grid size you use. But usually, if we want to have some numerical simulations in coastal zones, depending of what you are studying or what you want to research, we should say that usually we should use 100 meters as spatial resolution. So for that, we use the nesting procedure, and usually, well, we can get boundary conditions for the high-resolution nested grid from other models like WAN or WaveWatch3 in order to perform high-resolution simulations with the SWAN model. But I need to point out also that nowadays, you can perform any high-resolution simulations nearby the coastal zones also using WAN or WaveWatch3, because they also, at the beginning, these two codes were developed mostly for the deep waters, and the SWAN model was developed just for coastal zone or regional applications, but now we can perform a high-resolution simulation with all of three spectral wave model shown here. So wave model also need high-resolution current fields in order to properly resolve wave height gradients due to currents. So I brought this example because CCI C-state database is a very useful database. It's an homogenized data, and but still a little bit coarse in order to perform, for example, assessment of wave power using altimetry. So to the right hand is represented the mean map for the 26-year period. And as you can see, there are a lot of places where we don't have information, unfortunately. And for this reason, we need to use satellite altimetry data processed with this SAMOSA Plus algorithm in order to get more valid data nearby the coast. But because usually if we don't use or if we don't apply this retracker, then we have few information nearby the coast where we need this information. So in particular, I would like to speak about the cryosat mission processed with the SAMOSA Plus, which is bringing a lot of benefits. As you see from this map, only for 2 years we have a great coverage in the French facade region, and in the middle I compare some along tracks the wave power obtained from this mission against current speed. The French facade is characterized by a strong tidal current. So this is a very important information because we could say in the future, if we can recuperate energy from wave, just knowing what is the time of tidal currents. So what ESA is doing for wave? ESA is doing a lot of things. Among of them, it is running now the SAR wave model, which aims at developing a new C-state processor from SAR images to be applied over the open ocean, sea ice, and coastal areas, and exploiting potential synergy with other microwave and optical Earth observation products. So this is a good project, and also they are performing some development of experimental swell estimates from radar altimeters based on fully focused SAR spectra. So all the physical processes of wave that take place in the coastal zone need to be better monitored using the advantage of all available data that ESA is funding. So high-resolution data could benefit SAR wave projects in this sense, and using the Earth Console Altimetry Virtual Lab, funded by ESA also, we can process this data, and we can see that on very high resolution of 8 Hertz, that it is about 80 meters of unfocused SAR and fully focused SAR. So satellite high-resolution altimetry products are needed for this kind of research or applications, and together with high-resolution spectral wave modeling. So these both approaches are complementary. So I also would like to speak about benefits to SAR wave project. I would recommend some spectral high-resolution simulations for all the regions that are focusing the attention, such as Mediterranean Sea, Agulhas current system, French facade, or Iberian Peninsula. And also an added value is the fact that we own very high resolution data near the coast, spaced at 300 meters for all the Atlantic coast. And this data comes from the OCRE call of 2022. We want 200K to process Cryosat data and the Sentinel-3 with the SAMOSA Plus retracker. So the assessment of wave energy resource would be a good plus for SAR wave using high-resolution altimetry products. And this information is on demand with the present energy crisis, and could be used by different society stakeholders, such as local renewable energy companies. So we also would like to recommend to perform trends of the significant wave height and sea level rise. And this estimation using SAMOSA Plus high-resolution data would be a good plus. And this is a research that is running in collaboration with Legos, with Dr. Anik Casanave, and we should understand whether wave setup contributes to coastal sea level trends. So is there any trend in the wave setup that affect the sea level? This is a question to be answered. And this, to the right hand, I represented the significant wave height trend for using a wave buoy for the Spanish Port Authority in Cabo Silleiro in the Atlantic coast. So we need to better understand the wave and tidal current interaction as well. So finally, I would like to give some recommendation to the agencies. I recommend to ESA to launch more calls on WAVE to perform research and to support the activity. And in the present context of the energy crisis, accurate renewable energy assessment near the coast is needed. So we ask to ESA to support the development of this research activity. And also, I would like to recommend to ESA and other space agencies to support the creation of coastal altimetry products to fill the gaps in the coastal zones with the highest possible resolution, if possible, approximately 100 meters. So this is a big challenge, of course. And the quality of existing coastal satellite products need to be improved and verified with other observations. And to the in situ data agencies, such as Port of Authority of Spain, I would like to recommend installing more wave buoys to monitor the African coast in the Mediterranean Sea, where the assessment of wave power is needed urgently. Also in another coastal zones of the Atlantic Ocean. So we need to increase the number of the wave buoys in order to assess the quality of the coastal altimetry product, of course. So a large gap between the wave modelers community and the coastal satellite altimetry community exists. So regarding wave, so we need to improve the way of diffuse all the coastal products. And also it is needed a real-time coastal altimetry product for the operational wave forecast and high-resolution spectral wave modeling and coastal altimetry need to be complementary to better understand and predict coastal hazards. Thank you.
Thank you, Sonia. Any short questions? No? Okay. Yeah. Oh, sorry, Lachlan. If you could move to one of the microphones.
Thank you, Sonia, for your summary. Just a comment on the issue for the coastal area is the wind process related to generating very small waves, which really enter in interaction with the swell coming from the larger scale and also the current. So how about coastal winds inside all this process near the coastal zone?
What?
Coastal wind.
Coastal wind, coastal wind also is a lack, but there we have some wind fields. For example, the Wolf model, which has a spatial resolution of 1.5 kilometers. And this is an important subject, but also if we apply very high resolution near coast, we also are imposing some boundary conditions in the borders. So in that scales, the wave are somehow dominated by the wind, but also mostly from the information that is coming from the borders.
Okay, thank you. I think we'd better move on because we're 20 minutes late already. So thank you again, Sonia. So we're starting the first session, which is technical issues in coastal altimetry. So all the talks are 20 minutes each. So we'll give you a reminder. If you finish in advance, then there's some time for questions. And I'll give you a reminder 2 minutes before. If you take all 20 minutes, then we'll probably move on so that we finish in time for lunch. So first, it's Florence Biron from Lagos and round-robin assessment of altimetry algorithms for coastal sea surface data.
So, hello everybody. I would like first to say that this work has been done with different colleagues from Lagos, but also from CNES, Noveltis, and from CLS. And it has been decided after much discussion altogether on how we could improve the quality of coastal altimetry data. So what we have finally decided is to perform a round-robin exercise with the algorithm which are used to compute the seafloor side and focusing on the coastal ocean. So this work has two objectives. The first one is to gain insight on the sea level components that limit the most data quality near the coast. And the second one is to define a baseline for the generation of a new global coastal SLA sea level anomaly product. So concerning the definition of the round-robin itself, we have decided to focus only on conventional altimetry in this study, as a first approach at least. We will focus on the SLA variable at 20 Hz and consider both JSON2 and JSON3 missions. And we will use 3 years of data for each of them. So the analysis have been made both at global and at regional scales. And for the global scale, we have used all the data which are located between the coast and 200 kilometers offshore. And for the regional scale, we have considered 3 areas, the Mediterranean Sea, the Northeast Atlantic, and the Eastern Australian region. So in this table here, you have in the first column all the sea level components which have been included in the round-robin. And for each of them, in the second column, you have the list of the algorithm which have been tested. So the ones which are here underlined correspond to the algorithm which are used today to compute the standard sea level anomaly products. And they will be used as our reference in this round-robin. So just for information, the main selection criterion that we have used is that the algorithm had to be available at a global scale for both JSON2 and JSON3, and of course over the whole time period considered. So finally, we have tested a total of 24 algorithms in this study. So for each of them, we have computed a number of diagnostics, both at global and at regional scales. And these diagnostics have been defined with 3 complementary objectives. The first one is that for each algorithm, they had to measure the internal consistency compared to the reference solution, and also its performance in terms of SLA data availability and variance reduction, and this as a function of distance to the coast. So in practice, we have defined a number of statistics that you see listed here. So the second objective is that we wanted to use independent observations to measure the impact of each algorithm on the SLA calculation, and it has been done locally using tide gauge, a number of tide gauge data. And objective 3, we also wanted for each algorithm to measure the consistency of all the results we had between different altimetry missions. And this is why all the diagnostics have been systematically done for JSON2, JSON3, and intercompared. So just for information, we are preparing a specification document with all the details, and it will be made freely available soon. So now we move on to the results, starting with the wet tropospheric correction. So here I will show only results for JSON2 and at global scale. So for this correction, we have three solutions. We have the radiometer, which is here in blue, the JPD Plus, which is in green, and the SMWF, so the model solution, which is in yellow. And what you have at the right correspond to the standard deviation of the solution itself, which is represented as a function of distance to the coast for the three solutions in global average. And this is between 200 kilometers and 20 kilometers from the coast at the top, and between 20 kilometers and the coast at the bottom. And here, for illustration, you have at the right a map of the differences in standard deviation of the JPD plus minus the standard deviation of the radiometer. So what we observe here is that in terms of the standard deviation of the correction itself, the differences that are observed between the three solutions for the wet atmospheric correction are very small, with values which are below 0.3 centimeters. And if we focus on the radiometer and the JPD plus solution here in blue and in green, we see that the differences are very small, up to 7 to 8 kilometers from the coast. So now we look at the impact on this correction on the SLA itself. And at the right, you have the standard deviation of the SLA as a function of distance to the coast if we use one algorithm or the other. And this is between 200 kilometers and 20 kilometers from the coast at the top, and 20 kilometers to the coast at the bottom. And at the right, you see the differences in standard deviation of the SLA between all the solutions. So what we see here is that the impact on the standard deviation of the SLA, if we use one solution or the other, is below 0.1 centimeter near the coast at global scale. Of course, if we look at results more locally, we will have quite larger results. So to correctly interpret this result, we have to take into account two very important remarks, which would give an advantage to the JPD plus correction. The remark one is that concerning the radiometer, the results that we obtain are highly related to the processing version which is used. And here we have used a very recent processing version, but we could obtain results quite completely different if we used an older version or if we used another altimetry mission. And concerning, and the remark two is that the impact on the long-term SLA evolution, which is very important for climate studies and has not been included in this round robin exercise. So now we go to the ocean tide correction. And I will only present results for JSON3 at regional scale and more particularly for the Northeast Atlantic area. So for this correction, we have tested 6 model families, and for some of them, we can have different solutions. This is the case for phase. We have phase 2014, and we have also phase 2022. And for each of them, we have a gridded and an unstructured mesh solution. So the diagnostics, which is shown here, correspond to the residual sum of squares. So what does it correspond to? It's just a measure of the sea level variance, which is not explained by the ocean tidal model tested. If we take altimetry at the right or tide gauge, at the left, or tide gauge at the right as a reference. So you have one color for each model solution. And what we observe here is that the lowest RSS values, which are assumed to correspond to the best model performance, are observed for phase 2022 in its gridded or unstructured mesh version. So now we go to the range and the SSB corrections, which are considered together because they are highly related. Indeed, they are computed from fields which are deduced with the same tracking algorithm. So here we will, I will show you only results for JSON3, and here again at global scale. So we have 3 solutions. We have MLE4, which is the standard ocean tracker. We have the adaptive, which has been developed by CNES and CLS, and the ACE tracker developed by Passaro et al. So, sorry, the MLE4 is in blue, adaptive in green, and ACE is in yellow. And we consider first the results in terms of the SLA data availability. So here at the right, you have the number of SLA data. We have finally, as a function of distance to the coast, between 200 kilometers and 20 kilometers from the coast at the top and 20 kilometers to the coast at the bottom. So we see here that compared to the other trackers, MLE4 in blue stalls at 10 kilometers to the coast. And in comparison, if we use the adaptive or ACE, we recover significantly more data within the last 10 kilometers. And in terms of the number of coastal SLA data, ACE appears to be the most efficient algorithm. So now we look at the results in terms of SLA variance reduction with two important remarks. The HFA correction, which has been developed for the adaptive and its equivalent for ACE have not been included in this study. They are not used to compute the sea level anomaly. And for each solution, the SSB, which is used to compute the SLA, correspond to the tracker, of course. So here at the right, you have the standard deviation of the SLA as a function of distance to the coast, here again between 200 kilometers and 20 kilometers from the coast at the top, and 20 kilometers to the coast at the bottom. So here what we see is that this time the differences which are observed in the standard deviation of the SLA is much more important than before. We have values around 1.5 centimeter offshore, which increase up to 15 centimeter at 4 kilometers from the coast. Between 15 kilometers and 200 kilometers from the coast, the adaptive retracker in green gives clearly the lowest values in terms of standard deviation of the SLA. But between 2 kilometers and 15 kilometers, if we forget MLE4, which is not significant because it loses too many data, the ACE tracker this time gives the lowest values in terms of standard deviation of the SLA. And this is the reason why when you look at the results in terms of statistics of the tide gauge, which are not shown here, ACE tend to give slightly better results. So before concluding, I would like to go back to the two objectives of this work mentioned at the beginning of this talk, sorry, and put the results we had in this study in perspectives of each of them. So here I have summarized the results in terms of standard deviation of the SLA. And in the first column here, you have the different sea level components which have been included in the study. In the column 2, you have the differences in standard deviation that have been observed when we change one algorithm by the other. And in the third column, you have the areas where these differences are observed. So the numbers you have here just correspond to a first analysis, which will be refined, but what it shows quite clearly is that the range and the SSB are really the most critical components for the data, for the quality of coastal altimetry data, and this is true at global scale. The ocean tide and the mean surface height are also very important, but more at regional to local scale, sorry. The objective 2 was to define a baseline for the generation of a new global coastal SLA product. In this table, as a reminder, you have the list of the components and all the algorithms we have tested. And the ones which have been finally selected are indicated here in red. So for the range, we have chosen the adaptive because it is the one which gives the best results on the entire 0 to 200 kilometer coastal band. For the SSB, we will take the corresponding adaptive 3D solution. For the ionospheric correction, we will take GIM. For the wet tropospheric correction, JBD+. For the ocean tide, we have selected FES 2022 in its unstructured mesh version. And for the mean surface height, we will use CNES 22. So you see here that in comparison to the standard baseline, which is underlined, it makes really a significant number of changes that we really hope will, and we think will make the difference in terms of data quality near the coast. So as a conclusion, in this work, we have developed numerous reporting tools which are now available for future analysis, typically to test a new algorithm in the future. A summary of the protocol and of the main results will be published soon. But the most important result of this work is that a new global product covering the 0 to 500 kilometer coastal band and the JSON-free mission will be released very soon, in a few months. And here my main message is that we really will need your feedback to make this dataset a persistent product that fits your needs. But we have also some recommendations for space agencies. And my first one will be the need of altimeter corrections at 20 Hertz in L2 products. And we really think that it can make a difference for the quality of coastal altimetry data. So to support this request, I will just show one more and last example, result from the round robin. And it concerns the SSB correction for JSON2. So here we have two SLA datasets. The first one has been computed using SSB calculated directly at 20 Hertz, and the other one has been calculated calculated with the SSB compute at 1 Hertz and then interpolated at 20 Hertz. And here you have the difference in standard deviation of the SLA between the two. So only the SSB change in this case. So what we see here is that the SSB, when we compute the SSB directly at 20 Hertz, we reduce the SLA, the standard deviation of the SLA by about 0.4 centimeter in average, compared to when we use an SSB compute at 1 Hertz, which is the common case. And this impact is observed in the entire 0 to 200 kilometer coastal band at global scale, but it tends to increase in the last few kilometers. If we look at these results in terms plotted as a function of distance to the coast, which I have not shown here. Okay, so for my slide, my last slide, I have put all the list of recommendations we have for space agencies. I don't intend to read it now, but I hope we will come back to that during the discussion tonight. So, muchas gracias.
Thank you, Florence. Any questions?
Thank you. I appreciate this point about the need for CalVal sites in the cross-shore direction, especially for these coastal things. Do you have any ideas of what types of sensors and frequencies you would try to place to accommodate that?
Sorry, I didn't.
In your point up here about needing instrumentation in the cross-shore for calibration and validation.
Yeah.
Thank you. Do you have an idea of what instruments you would need and what frequencies that you would need them to operate in?
I will say a bottom pressure sensor, for example.
I was hoping you would say wave buoys also.
Sorry?
I was hoping you would say wave buoys also.
She said she was hoping she'd say wave buoys.
Wave buoys.
Yeah.
Yes. Wave buoys, yes, to be interesting to to be sure that maybe the correction we apply in terms of SSB is correct. But here, what we really would like to validate is the sea level we compute at the end. We have a number of tide gauges which are commonly used, but they only provide a reference at the coast, and most of the time they are not located at the same place. And as you know, the coastal dynamics is changing very rapidly in space and time. And so it's very complicated to compare tide gauge observations at one place and altimetry data at another. Very complicated. And also now we start to have altimetry data quite close to the coast, and we see a number of changes, a number of signals, and for the moment we have no idea we are not completely sure that it corresponds to signal, or if it's errors or noise or something else.
Okay, thank you. I think we better move on. So the second presentation of the session is from Zulfikar Nadzir from the University of Bonn on coastal altimetry datasets performance in Indonesian seas.
So, good morning, everyone. My name is Zulfikar. I'm a PhD student in the University of Bonn. And today I would like to tell you a short story about the performance of coastal altimetry datasets in Indonesian seas. But before we start, let me tell you the results of the research so then we can skip into the coffee break, I hope. The first one is that it turns out different read records, this one is coastal read records, have comparable performance. And second one, it turns out that the geographical and oceanographical situation could play a role in a read record performance. And this presentation is based on a first year work of my PhD, and it is a continuation, so to say, from last year EGU presentation, which was done also by me. Now, if I could start with why do I wanted to do this study? So on the last 20 years, as we all know from the Bible at the front, there are a lot of efforts have been done to improve the coastal altimetry or altimetry at the coast. And mainly they're basically about two things. The first one is to somehow to develop dedicated corrections for coastal area. And second one is about designated retracking. And two of the results of those advancements, so to say, is ALES, or it is a adaptive retracker that was I think developed by Passaro in 2014. And also there is a coastal dataset which are called Extract ALES that was presented yesterday, I think, in the afternoon session. However, those coastal datasets were always validated separately, in the sense that they always separate the ALES itself with tide gauge, Extract ALES itself with tide gauge. And there are several studies that were exactly pointing on that direction, where so for example, ALES in Passaro has tried in several years in many locations as well as for Extract ALES. Now, the main question about this is how, if we compare the retrackers together, so not separately but together, and also utilizing high frequency tide gauge. And that's exactly my objective here, to compare coastal datasets on Indonesian seas using high frequency tide gauge stations in Indonesia, which maybe some of you are aware that available but inaccessible in some cases. So in this case, I'm using 24 hourly tide gauge data in Indonesia, which are available thanks by Indonesian Geospatial Agency, or Badan Informasi Geospasial in Bahasa Indonesia. And I divide that into 3 locations according to the geographical and oceanographic conditions. The first one, mainly on the left side, is the green one, is the near subduction zone groups. The second one is the shallow coast, or I could say a flat coast, are in the middle, and it is colored yellow, and also for the far right one is the Indonesian throw flow, which are colored blue. Now let's continue on the datasets. So here I'm using 3 datasets. The first one is extract ALES, or some might say it's SLCCI plus. It spans from 2002 until 2018. And I'm using, in the filtering sense, I'm using the data that only flag OK or 0, according to the latest user guide. And second one, I'm using data, ALES data, which are filtered according, again, to the recommendation. So 3 kilometers from the coast, and there's several thresholds based on the SSH and MSS and also SWH, sorry. And lastly, as a reference, I used a data from KIMEMS, the Copernicus Marine Surface. Since there's no flag and there is no recommendation inside the user guide, so I assume that the data were already corrected and also, so to say, filtered to be able to be used not only in the open ocean, but also from the coast. And for all those 3 datasets, I harmonized the model, but I will not explain the model in detail in this slide. Now, going back to the how to build the time series, Professor Jesus Gomez Henry has already explained to us many of the ways to build the time series. And in my case, I'm using a nominal point method. So basically, it is based on a long track product. And then I use reference data, in this case, 1 Hertz reference point, to then finding a data inside a 3 kilometer radius. And out of those 3 kilometer radius, I average the data inside those radius to then build the time series. And this is actually connected to the first parameters that I use to quantify the precision. I call it internal noise level, which represents the standard deviation of the average data. This is my way of saying, okay, this data are quite smooth, or in a sense, quite precise compared to the others. And now talking about the evaluated parameters for the tide gauge data, I'm using SLA tide gauge. So it's my way of saying that I'm reducing the mean of the tide gauge data by the mean of each time series of the tide gauge. And for the altimetry data, I'm using the TWLE, or the total water level envelope, which represents the instantaneous, so to say, water level that was observed, which being included with the DAC and tied back into the data itself. And I use several performance parameters or performance metrics. The first one is, as I said in the last slide, an internal noise level for precision. And second one, for accuracy, I also use number of observation, Pearson correlation coefficient, and also standard deviation of difference and median absolute deviation of difference. Additionally, I also use a short group-based analysis, which will be our, so to say, second part of the results. Now, coming to the first results, the internal noise level, it can be seen from the scatter plot here that the ALES, which are in orange, and extract ALES, which are in yellow, are more or less having a lower internal noise level. And if we quantify it, it somehow improves the noise level by around 69%, from around 40 centimeters on the nominal data to an average 15 centimeters for both ALES and extract ALES. Now we go to the number of observation. It turns out that out of the 24 tide gauge that we use here, there is a varying number of observation, but in average, those 3 datasets have data for each point around 100 in magnitude. And we could also see here that in average, extract ALES data has the highest number of data, followed by ALES, and then KIMEMS. Now the third one is about correlation coefficient. We can see that again, it differs greatly for several tide gauges, and I really need to take a look into that, why it happened on the, for example, Sublat or also Waikilo has some problems with the processing itself. but I still show it here. But in average, all three datasets perform similarly with the correlation coefficient in average of 0.8. And again, it can be shown that the extract ALES outperforms other datasets. However, I need to point out that ALES placed third, or so to say, performs worse than the nominal data here. And talking about standard deviation of difference, we can also see here that the yellow or the ALES are somehow stand out. So that what I wanted to point out again, that ALES performs the third or performs the worst in this case of the 22 tight gauge stations. Whereas for the extract ALES and nominal data, the results are, so to say, we can say it's quite similarly, around 18 centimeters standard deviation of differences. Now, we went to the median absolute deviation of difference. It was a matrix that was suggested by Marcello Passaro after the EGU 2022 presentation, and it's found that in average, all three datasets performs alike. But in this case, nominal data has, so to say, the smallest MIDD among others, whereas extract ALES performs, so to say, the worst. But in this case, the difference are not that big. It is 6.1 centimeters for nominal track. For extract ALES is 8.3. Now, if you want to do an overview out of the performance metrics, so please focus on the left side of the table here. We can see that out of those 5 performance metrics, so to say, XA and NM, extract ALES and nominal data performs well across the performance metrics. For some, they have slight differences, but for others, extract ALES is the clear, so to say, winner here. And if we see at the right side of the table here, I tried to take a deep look into the different group I mentioned before on the location. So I need to remind you that the first one is the one near subduction zones. The second column is the flat coastal zones. And the third one is the Indonesian through flow zones. And from that, we could see that all retractors performs the best on the group 2, or we can say that in the flat coastal zones, all retractor performs the best compared to the one with steep bathymetry in a sense, and also where there is a huge or a strong current. And a bit of additional result, since SAR data has become a trending topic in coastal altimetry nowadays, I also compute the sum plus plus as sum plus compared to the KMEMS data, and it found that the sum plus plus outperforms sum plus. Meanwhile, the SAR data, in this case, unfocused SAR, I haven't reduced the fully focused SAR yet, have smaller magnitude of standard deviation compared to the LRM mode results. 13 centimeters versus 20.5 centimeters. So the conclusion is, going back to the spoiler alert slide before, turns out that the coastal retractor are more precise. And then, but in accuracy terms, extract ALES and KMEMS perform on similar level. And the third one is location with steeper bathymetry slope or strong current perform slightly worse compared to the location on the flat coastal zones. And lastly, comparison shows that in terms of standard deviation of difference, SAR data performs better than the LRM counterpart. Now, some outlook and recommendations. The outlook is, first, we need to add more SAR datasets into computation to then not only taking a look and compare between the coastal or different datasets, but also different observation modes. And secondly, what I personally wanted to do now is to expand the study among 45 more additional tight gauges, because unfortunately I have an access to 40 plus 45 additional tight gauges in Indonesia now. And 3, based on the results on the groupings, I wanted to go and do a deep dive into the effect of bathymetry and topography of the coast, waves, and possibly tides on the coastal sea surface height retrieval. And I do have one recommendation. It's not written here, but I think for not only the space agency, but also for the national, maybe geospatial agency, it would be beneficial for all of us if we could start to talk more, if we could start to coordinate more, so then everyone, so to say, could provide or could contribute to for the data, because sometimes for the third world, or then, so to say, in the developing world, the availability of the data are really sparse. Although we say, yeah, it is a global study, but then so to say, the validation pace or validation point for the developing world is not that much. And that's it for me. If you have any question, please ask or email me at natsir@unipon.de.
Any question?
Thanks. Nice talk. Not to add more to your work list there, but one other thing that maybe you could look into would be the vertical land motion correction in the subduction zone, because that might be, I mean, it might not be the retracking so much as the side correction.
Great. Thank you for pointing out that. I'm actually on my way on computing the coupled GPS vertical land motion out of those 24 tide gauges, and I hope that later in the year I could then get a manuscript out of those. Thank you.
Thank you very much for your presentation. Is there any special reason why you use the total water level envelope instead of sea level anomaly? It's because you don't trust in the tidal model in your study area? Or?
That is actually a great question. Why I use the TWLE here, because the tide gauge itself are, so to say, if I put the tides and everything, if I corrected the tide gauge, it would be, I mean, I wanted to do that, but for now I'm still using the TWLE. But you're right, as you mentioned yesterday, there's some other parameters, and one of them the SLA. I will actually do that, and if I have the results, I will tell.
I think it's a complicated area. Your study area is a complicated area for the tidal models. I don't know if you have made any analysis of which model would be better in your study area.
I haven't checked yet. We do have, as an information, we do have a local tidal model based on the tide gauge, but I really haven't checked the performance out of those models.
Okay. Thank you.
Thank you.
Okay, thank you. So we move on to your talk, David.
Okay, so apologies to those of you who saw the training yesterday. So some of this material will be repeated, but maybe there's a better chance of it being remembered. So this is about the hydrocoastal project, looking specifically at SAR altimetry and how to improve altimetry processing over the coastal zone. So hydrocoastal is funded by ESA through its Science for Society program. And the idea is to particularly look at SAR and SAR-IN altimeter data measurements in the coastal zone and also over inland waters, and looking at new retracking algorithms, particularly for SAR data. So we've applied 6 different new algorithms for retracking algorithms for SAR altimeter data over the coastal zone and inland waters. And we implemented them, we've evaluated them, and then on the basis of that evaluation, we selected the best performing, and we're in the process of now generating a global scale coastal zone and river discharge set. And the final aspect of the project will be to run some case studies to assess those projects. There's 15 partners in the hydrocoastal. You can see all their logos there. I won't read them all out, but just want to acknowledge all of their contributions. So the project's got 4 phases to it. We started with a scientific review, looking at the current state of the art in SAR and SAR in altimeter data processing, and there's a technical note with that review. We're hoping to turn that into a paper, just waiting to find the time to do that. Then in the second phase, we implemented these new reprocessing algorithms, generated a 2-year test data set. We evaluated the performance of those algorithms, and as I said, we selected the best performing to generate a final product. We're in the process of doing that now, and then when that's available, we'll be carrying out these impact assessment studies, item 3 there, through a series of case studies. And then we'll finish, hopefully in June this year, with a roadmap with recommendations for further research and development and recommendations for implementing in current and future SAR altimeter missions in terms of new processing schemes. So the first hydrocoastal test data set covers 18 regions of interest to provide a wide range of different environmental characteristics for inland water and coastal zone. Covers 2 years for most areas and 3 years for some where we were doing river discharge estimates. The inputs are Cryosat FBR baseline D data and Sentinel 3A and 3B SIRAL data. And we've also used the enhanced wet and dry troposphere corrections provided by the University of Porto with their GPD plus scheme that Florence mentioned earlier. So there's descriptions of all of the different processing schemes and products available. We've got a big algorithm theoretical basis document which describes them all. So if you go to the website, you can find them. Those are the 18 different regions, so split pretty much for the test data set, split pretty much evenly between rivers and coastal regions. As I said, we tried to cover a wide range of different environments to give a proper assessment of which of these different algorithms, different processing algorithms. And the 6 algorithms are listed there on the left. Some are specifically coastal, some are, I suppose the idea is to work that both work over coastal and inland waters, and some are specifically inland water algorithms. So the ESA-ESRIN 2-step processor is, the idea is that will work both coast and inland waters. There's a SARIN algorithm for Arasis, which is just for coasts. There's the DTU multiple waveform persistent peak algorithm, which is designed for inland waters. There's the along track isolate, cleanse, classify, empirical retracker, so that it sorts the multi-peaked waveforms out, and that's specifically for inland waters. The University of Bonn statistical stars type retracker, and then there's the AILS Plus, so it's the AILS algorithm, AILS retracker from Unit, from Marcello Passero, but it configured for SAR altimeter data. So all of those algorithms were run on the same input data sets, and we've generated a combined product with all of those within it, and that's actually available now. So if anybody wants to see that, to use that and have a look at it, they can just send an email and we'll give them the link. And that data set was evaluated for the coastal zone with 4 different in 4 different areas by 4 different partners, and we're looking specifically at the DTU reprocessor, the ESA-ESRIN reprocessor, the AILS Plus reprocessor, and the University of Bonn stars type reprocessor. So we compared all of those 4 together in different areas, so over the German Baltic Sea, the California coast, near the Harvest platform in southern Spain by Jesus, and by doing a look at how the statistics vary as we get closer to the coast over all of those different zones. Don't have a time to go into all of the results, but essentially in terms of sea surface height, we looked at the sea level anomaly and compared that to measurements from tide gauges in different regions. Calculated the standard deviations of difference between the tide gauges and altimeter data, and then averaged that between 2 to 20 kilometers from the coast. Results varied from region to region, so getting the lowest standard deviation differences in the California area, and the highest up to 17 centimeters in the German Bight and the Baltic, and a wider range for CryoSat-2 data. We found that different retrackers performed better in different regions, and none was consistently better than any of the others. But what we did find a difference in terms of significant wave height, but only 2 of the retrackers, the University of Bonn and ESA-ESRIN retracker, provided significant wave height and wind speed. And then we found that the Bonn data were consistently better than the ESA-ESRIN data. So on that basis, that the sea surface height data, there was no one retracker stood out as performing better than the others, but the Bonn retracker performed better in terms of getting significant wave height. We selected the University of Bonn retracker for implementation in the next phase. And after Sonia's talk this morning, I'm glad that we did place that focus on significant wave height. There's some very quick overview of results. If you want to see them all, we've got a product validation report. But just to give you a kind of flavor, so this is from the validation carried out by Luciana and her colleagues at the University of Bonn. So on the right-hand side, moving from right to left as we get to the coast, you can see the performance of different retrackers in terms of noise and number of points retrieved. And so we have the Bonn retracker on the top left, DTU tracker on the top right, the ESA-ESRIN retracker on the bottom left, and the TUM, so the AILS Plus retracker on the bottom right. And you can see that for the Bonn retracker, we kind of get the lowest noise. This step, which there's a kind of change of mode in that. But that suggested that actually we get more data retrieved closer to the coast with a lower noise from the Bonn retracker. And then the results from the validation against tide gauges, probably don't have time to go into all the detail, but you can see that we get different results, interestingly, for Sentinel-3A and 3B as to which retracker performed the best, but they were all pretty close. There wasn't an awful lot between them. And then when we looked at the buoys, as I say, we found that the University of Bonn retracker gave us the lowest, best correlation, lowest RMS when we compared it to buoy data. This is for the California data set that Francisco Calafat did for NOC. But interestingly, the original ESA data gave us the best results for wind speed. So from that evaluation, as I say, we selected the University of Bonn retracker for the coastal zone. We selected the DTU retracker for inland waters. Don't have time to go through the evaluation of that product. And we're in the process now of generating a global scale coastal and river data set. We're using a virtual machine provided by Earth Console. We managed to get sponsorship for that. And yeah, so we'll provide a global scale level 2 data set for the coastal zone and inland waters, and then level 3, so time series for selected large to medium rivers, and a river discharge data set for those rivers, and an experimental data set for smaller rivers. And we hope this product will be available in the next quarter, so from April onwards. Again, that'll be available for anybody who's interested to see it. The initial coverage for this product is for the regions in the table there. That's where we're carrying out the impact assessment studies. We'll process all of the Sentinel-3A and 3B missions, and then the CryoSat-2 mission where baseline D data are available. So that's up to mid-August 2021. It's a net CDF format, what we're calling, it's an internal format, level 2 enhanced, so it includes the outputs from the 2 retrackers and the original ESA data. If you've been interested in receiving data for other regions, and maybe you want us to cover the Indonesian seas, for instance, then let us know, and we'll try to add it to the list. We have this is our initial list of proposed additional areas. Basically, we're going to go down as far as that as we can with the funding and the time that we have. the idea is to focus on where rivers meet the coast so that we can kind of fill in the gap, if you like, where the river discharge goes into river estuaries so that we can bring together a consistent data set for those regions. But again, if you want us to add some regions, or if you want to encourage us to push up the priority of any of those regions, then let me know. Finally, I think just a quick review. So these are the impact assessment studies that we're carrying out to test and demonstrate the benefits of this new data set with what we believe are the best new processing algorithms. So we've got a series of processing case studies, which are looking at some technical aspects of processing. We've got those 6 coastal inland waters, so coastal zone studies at 7 estuary, Baltic and German Bight, with the Elbe estuary, the Venice Lagoon, Thailand coast, the Ebro River and Delta, and the Wadden Sea. So looking at those regions, and then we've got some inland water case studies on a kind of larger scale, really looking at how well they perform for those uses. So what we'll provide as outputs from the project, we have the state-of-the-art review. We've got the initial test data set over 18 regions with those 6 algorithms. We've got descriptions of all of the processing algorithms and the output products. We've got the product validation report, and then we'll have these global scale output products. As I say, they won't be truly global because we're limited by the resource we've got in the project and the time left of us. And then final output will be a scientific roadmap with recommendations for further developments. And as I asked everybody else to provide outlook and recommendations, I thought I better had too. So just to say that these 2 data sets are available. Because we're using Earth Console, we've got a scalable processing solution, so we can add regions to it if we can make resources available. As I said, if you want to access the data, contact me, or if you want us to try and include other areas in the processing, also contact me. I said that the scientific roadmap is going to provide recommendations for further improvements to processing and to generate an improved global scale SAR altimeter coastal inland water data set. But just some points to note is that the along track nature of altimeter data, as everybody knows, it can limit uptake by users because of its kind of sampling, intermittent sampling and coverage. So I think we need further investigations on how to derive gridded data that's useful to users. It'd be interesting to look at the impact of freshwater river discharges on sea level variations in the transition zone between estuary mouths and coastal waters. And we found that different read trackers perform better in different locations and environments. So how do we make the balance between a consistent data set with a single read processor to using the read trackers that perform better in different regions? And that's me finished, so welcome any questions. Thank you.
Thank you, David. Is there any question? No question? You were very clear.
Yeah.
You were very clear. There is no question.
Okay.
Okay. Thank you.
Sorry.
No, you have no question. We have an announcement to do. You have to get your social event ticket now during the coffee break.
Okay.
The ticket for the social event. If you don't have your ticket, you have to get it now.
Okay, so we'll break for coffee. 20 minutes, so if we start again at 20 past 11. If you've got presentations for the next session, please bring them up now so that we can have them ready for the beginning.